Good morning to everyone present here. I'm welcoming to the video session on the topic Analysis of Refrigeration in Aeroengineering Thermodynamics. Myself N. Venkatesh, working as an assistant professor in Department of Aeronautical Engineering, SNS College of Technology, Coimbatore. This is the learning objectives of in the refrigeration. First of all, thermodynamic heat pump cycles or refrigeration cycle are the conceptual and mathematical models for heat pumps and refrigerators. A heat pump is a mechanical system that allows for the transfers of heat from one location at lower temperature to another location. Thus, a heat pump may be thought of as a heater if the objective is to warm the heat sink of refrigerator. If the objective is to be cool the heat source, in either case the operating principles are identical. Heat is moved from cold place to a warm place. According to the second law of thermodynamics, heat cannot spontaneously flow from a colder location to a hotter area. Work is required to achieve this. An air conditioner requires work to cool a living space, moving heat from the cooler interior to the warmer outdoors. Similarly, a refrigerator moves heat from inside the cold ice box to the warmer room temperature air in the kitchen. The operating principle of the refrigeration cycle was described mathematically by side Carnot heat engine. A heat pump can be thought of a heat engine which is operating reverse. Refrigeration cycle can be classified as a vapor compression and vapor absorption, gas cycle and Stirling cycle types. The vapor compression cycle is used most household refrigerator as well as in many large commercial and industrial refrigeration systems. The thermodynamic of the cycle can be analysis of a diagram in a reference. In the empathy section is a cold is not enough and unit is cycling to often defrost and faulty motor. The thermodynamic of a cycle analysis in a vapor compression system. The liquid refrigerant goes through the expansion valve where it is precisely abruptly decreasing, causing flash evaporation and auto refrigeration of typically less than that of one of the liquid. That results in a mixture of liquid and vapor at a lower temperature and pressure. The cold liquid vapor mixture then travels through the evaporator coil or tubes and is completely vaporized by cooling the warm air being blown by a fan across the evaporator coil or tubes. The resulting refrigerant vapor returns to the compressor inlet to complete the thermodynamic cycle. The above discussion is based on the ideal vapor cycle refrigeration cycle and does not take into account real world effects like frictional pressure drop in the system, slight thermodynamic irreversibility during the compression of the refrigerant vapor, or non ideal gas behavior. In the early years of the 20th century, the vapor absorption cycle using water ammonia systems was popular and widely used, but after the development of the vapor compression cycle, it lost much of importance of because of its low coefficient of performance. Nowadays, the vapor absorption cycle is used only where heat is more readily available than electricity, such as waste heat provided by solar collector or off the grid refrigeration in recreational vehicles. The absorption cycle is similar to the compression cycle, the except for the method for raising the pressure of the refrigerant vapor in the absorption system. The compressor is replaced by an absorber and a generator. The absorber dissolves the refrigerant in a suitable liquid and the delicate solution becomes a strong solution. In our ideate section, before we discuss about the define section absorbs heat from the food and absorbs the heat to the relatively cooler surrounding outside cooling. In the defined section, a gas cycle when the working fluid is a gas that is compressed and expanded but does not change phase. The refrigeration cycle is called a gas cycle. Air is most often this working fluid as there is no condensation and evaporation intended in a gas cycle. Components corresponding to the condenser and evaporator in a vapor compression cycle are the hot and cold gas to gas heat exchangers. For a given extreme temperatures, a gas cycle may be less efficient than a vapor compression cycle because the gas cycle works on the reservoir in Brayton cycle instead of the reservoir Rankine cycle, such as the working fluid never receives or rejects heat at a constant temperature. In the heat pump, it is the absorption cycle is similar to the compression cycle, the except of the method rising of a refrigerant vapor. When the working fluid is heat pump, reversible heat, and the four processes that compress it, two isothermal and two isentropic, can be reversed. When this happens, it is called a reversed Carnot cycle. A refrigerator or heat pump that act on the reversed Carnot cycle is called Carnot refrigerator or Carnot heat pump respectively. In the first stage of this cycle, the refrigerant absorbs heat isothermally from a low temperature source and the refrigerant is isentropically compressed and its temperature rises to that of the high temperature source. Then at this high temperature, the refrigerant rejects heat isothermally in the amount of heat rejection. The coefficient of a refrigerator heat pump is given by a coefficient of performance. The Carnot cycle reverse cycle is comprised of two and the heat pump is efficiency is described of a parameter called coefficient of performance. In ideate section, the compressor constricts the refrigerant vapor, rising its pressure and temperature, and pushes it into the coil of the condenser on the outside of the refrigerator. Here, it is mentioned about the heat pump will elaborately discussed in the Stirling engine. Heat can be driven in reverse using a mechanical energy input to drive heat transfer in a reversed direction. There are several design configurations for such a device that can be built. Several such setups require rotary or sliding seals, which can be introduced. Difficult trade-offs between frictional losses and refrigerant leakages. Here it is the Stirling engine performance will be explained. Here the COP is the relation between the heat transfer to the work done and the heat pump is relatively working between the refrigerator also. Here we'll explain about Stirling engine concept. Now gas cycle of the working fluid is gas that is compressed and expands but does not change phase. The refrigeration cycle is called a gas cycle. Air is most often this working fluid as there is no condensation and evaporation intended in a gas cycle. Components corresponding to the condenser and evaporator in a vapor compression cycle, there are hot and cold gas to heat exchangers. For given extreme temperature, a gas cycle may be less efficient than a vapor compression cycle because the gas cycle works on the reverse Brayton cycle instead of the reverse Rankine cycle. As such, the working fluid never receives or rejects heat at a constant temperature. In the gas cycle, the refrigeration effect is equal to the product of the specific heat of the gas and the rise in temperature of the gas in the low temperature side. Therefore, for the same cooling load, gas refrigeration cycle machines requires a larger mass flow rate, which in turn increases their size. In a prototype, we consider is a component arranging in the given big diagrams: condenser, compressor, valve and microprocessor. The Carnot cycle is a flow process. It is an isothermal and isentropic process, can be reversed. When it happens, it is called a reversed Carnot cycle. Here it is explained by the Carnot theorem. Well, the cycles are in the diagrams represented. The process 1 to 2 is a compression of vapor and the process 2 to 3 is a vapor superheated in condenser and 3 to 4 in a vapor converted liquid in condenser and 4 to 5 in a liquid flashes into the liquid plus vapor across expansion valve, and a 5 to 1 liquid plus vapor converted to all evaporator conditions. The graph is similarly drawn between the temperature and the specific heat. Here, the absorption cycle is similar to the compression stroke, except the method of raising temperature is refrigerant, the vapor. The four components of simplest diagram is an evaporation compression cycle is compressor, condenser, and evaporator, and this expansion valve. Here is a typical single stage vapor compression refrigeration is they explain between the evaporator and the valves will be connected to the interconnection, and the condenser the air is passed through the condenser and the liquid will be generated and flowed to the liquid plus water, and final the exhaust cold water will be released. The discussion is based on the ideal vapor compression cycle, does not take into a real world effects like frictional pressure, slight thermodynamic irreversibility during the compression of the refrigerant vapor, or on ideal gas behavior. In the early years, the 20th century, the vapor absorption cycle using water ammonia system was popular and widely used, but after the development of the vapor compression cycle, it lost much of its importance because of low coefficient of performance. About the one-fifth of that vapor compression cycle, nowadays the vapor absorption cycle is used only heat is more readily available than electricity, such as waste heat provided by solar collectors of the grid refrigeration in the recreation vehicles. The final condition of is a test is four main components are connected, and the final is electrical energy is used to pump heat out of the cabinet. The refrigerant is the working fluid that pass through the all components. This gas cycle will express no change. The refrigerant cycle is called gas cycle. Air is most often this working fluid, as there is no condensation and evaporation intended in a gas cycle. Components corresponding to the condenser and evaporator in a vapor compression cycle are the hot and cold gas to gas heat exchangers. For given extreme temperatures, a gas cycle may be less efficient than a vapor compression cycle, because the gas cycle works on the reverse Breton cycle instead of the reverse Rankine cycle. As such, the working fluid never receives or rejects heat at a constant temperature. In the gas cycle, the refrigerant effect is equal to the product of the specific heat of the gas and the rise in temperature of the gas in the low temperature side. Therefore, for the same cooling load, gas refrigeration cycle machines require a larger mass flow rate, which in turn increases their size. Because of their lower efficiency and longer bulk, air cycle coolers are not often applied in terrestrial refrigeration. The air cycle machine is very common, however, on gas turbine powered jet airlines, since compressed air is readily available from the engines. Compression sections. These jet aircraft's cooling and ventilation until also serve the purpose of heating, pressurizing the aircraft cabin. This is the our refrigerant how to working, and the efficient what are the efficient performance will be given in upcoming discussion. The equation of COP is relation between the heat transfer to work done. U is the useful of heat supplied or removed by the considered steam. W is the work required of the considered steam. The detailed COP of a refrigerator is given as desired output divided by the desired input, or else it's equivalent to cooling effect by work out input. The COP of a heat pump is given by the following. Its name as heating effect by work input. Both the COP of refrigerator and heat pump can be greater than 1. Combining these two equations result in COP of a heat pump is equal to COP of a refrigerator plus 1 for fixed values, high heat value and low heat value. The implies that the COP of a heat pump will be greater than 1 because COP of refrigerant will be positive quantitative. In a worst case scenario, the heat pump will supply as much energy as it consumes, making it act as a resistance heater. However, in reality, as in home heating, sum of heat values is lost to outside air throwing the pipe and insulation, etc., thus making the COP of heat pump drop below unity when the outside air temperature is too low. Therefore, the system is used to heat houses using fuel. For Carnot refrigerator and heat pump, COP can be expressed in terms of the temperature. For example, COP of a Carnot cycle will explained by it's the ratio of lower temperature to differentiation between the high temperature and lower temperature, and the COP of Carnot heat pump is a ratio between temperature of highest to the temperature of differentiation of highest to lowest. This is our testing condition of refrigerator, and that these are the reference links which shows us the how to the refrigerator works, what are the types used in this refrigeration, and which principles refrigeration work and applications will be derived in these reference links. Thank you.